Materials make distinctive sounds when you hit and scratch them. These sounds can tell us how objects behave when we physically interact with them. They can convey whether an object is hard or soft, smooth or rough, and rigid or deformable. In this work, we consider the material understanding task of predicting what sound something will make when you hit it. We give an algorithm a silent video of someone striking things with a drumstick, and we ask it to produce a plausible soundtrack to go along with it. To perform this task well, the algorithm has to recognize the materials that are being hit and the actions that are being performed, but we don't explicitly tell it about these things. Instead, it has to learn about them by recognizing patterns in the raw audiovisual signal. Our algorithm takes a video sequence as input, and it predicts a corresponding sequence of sound features. Then, it generates a waveform. We get these sound features by training a recurrent neural network to regress cochleogram features at each video frame. This is a simple sound representation that we obtain by decomposing the audio waveform into frequency channels with a bank of bandpass filters. To represent the video frames, we use a convolutional network. This network operates on ordinary color images, and it also obtains motion information using a space-time image representation. After our network predicts sound features, we synthesize a waveform by matching these features to a database of impact sounds and transferring the best matches. Here are some soundtracks that our algorithm produced. To help understand what our model's doing, we can look at the video clips in our database that it's transferring audio from. These are the audio clips whose sound features are most similar to those predicted by our model. Our algorithm can get confused when the motion of the drumstick resembles a hit, but it does not actually strike a surface. Our algorithm also sometimes misses hits, especially when the drumstick is held in an unusual position relative to the camera. Instead of synthesizing a waveform by transferring sounds from a database, we can directly invert the sound features with a simple parametric synthesis method. This can help us understand what information is contained in the sound features that our model predicted. In the paper, we analyzed our model in several ways. First, we asked how well the algorithm could predict plausible sounds. To answer this question, we conducted a human study where we asked people to distinguish real impact sounds from sounds that were synthesized by our model. For this, we trained a variation of our model that predicted sound for individual drumstick impacts rather than for full videos. We found that our sound predictions fooled participants more often than those of baseline methods, including simple image matching models. Next, we asked what the algorithm learned about materials. To study this, we collected a database of semantic labels from human annotators. Then, using these semantic labels, we classified the sound features predicted by the model, and we measured how often they had the correct label. Please see our paper for more details.